Hello, Chemistry 30. This is our fifth lesson in the equilibrium unit. This is the equilibrium constant Kc. In this lesson, we will explore the equilibrium constant, the Kc expression, also known as the equilibrium law, and we will work through 5 examples. The equilibrium constant Kc is a ratio between the concentration of the products and the concentration of the reactants at equilibrium for a specific temperature. Kc does not have any units. The value of Kc will remain constant for a chemical reaction, regardless of the initial concentrations. The only factor that will affect Kc is temperature. If temperature changes, Kc will also change. The Kc expression. If we look at the following forward reaction, where A and B are the reactants and C and D are the products, this is our Kc expression. The concentration of capital C and capital D represent the concentration of the products at equilibrium, where the concentration of A and B represent the equilibrium concentrations of the reactants. Lowercase a, b, c, and d represent the coefficients in the chemical equation in front of each chemical species. It's important to note that to calculate Kc, our concentrations must be at equilibrium. The Kc value for a forward reaction is always products over the reactants. For the reverse reaction, the Kc is the reciprocal, which is 1 over the Kc value. Kc provides us with important information regarding the equilibrium reaction. A higher value of Kc represents a greater tendency to favor the forward reaction. If Kc is greater than 1, the equilibrium system favors the products. If Kc is less than 1, the equilibrium system favors the reactants. And if Kc equals 1, neither the products or reactants are favored. That would mean that we have equal amounts, 50% of the products and 50% of the reactants. Consider the following. Solids are not included in the Kc expression. That is because solids do not affect equilibrium. If liquids are to be included in the Kc expression, all species in the chemical equation must be liquids. And finally, gases and aqueous states are always included in the Kc expression. Example number 1. Sulfur dioxide gas reacts with oxygen gas to form sulfur trioxide gas. Calculate the equilibrium constant Kc using the equilibrium concentrations below. Pause the video and attempt this example. First, we will need a balanced chemical equation where we can see 2 SO2 gas is reacting with 1 mole of O2 gas at equilibrium to form 2 moles of SO3 gas. We can then write our Kc expression, which is the products over the reactants. And don't forget, our exponents are the coefficients in the chemical equation. We can then put our equilibrium concentrations into the Kc expression. Thankfully, the question did give us our concentrations at equilibrium. This would give us the following values in our Kc expression. And when calculated, our Kc value is 0.284 at flask temperature. We state at a specific temperature because Kc is dependent on temperature. Example number 2. Write the Kc expression for the forward and reverse reaction using the chemical equation below. Pause the video and attempt this example. Remember, solids are not included in the Kc expression. For our forward reaction, our Kc expression is the concentration of CO2 gas over 1. And for our reverse reaction, the Kc value is the opposite, 1 over the concentration of CO2 gas. Example number 3. Determine the equilibrium constant, Kc, of the following reaction using the graph below. Pause the video and attempt this example. Our graph represents our initial concentrations at time 0, and eventually our system goes to equilibrium. Remember, we need equilibrium concentrations in our Kc expression, so we must take the following values when each chemical species has flatlined in the graph. Our Kc expression is the concentration of the products over the concentration of the reactants. And again, our exponents are the coefficients in the chemical equation. If we input the equilibrium values from the graph, we are left with a Kc value of 0.090 at flask temperature. Example number 4. Initially, 3.5 moles of ammonia gas are placed into a 5.0 liter flask and sealed. At equilibrium, there are 0.20 moles of hydrogen present. Are the reactants or products favored in this equilibrium? Pause the video and attempt this example. To determine if the reactants or products are favored, we have to determine the Kc value. And to determine the Kc value, we need equilibrium concentrations of all species. Unfortunately, this question does not provide this. Therefore, we need to create an ICE table and determine the equilibrium concentrations of each species. Initially, we have 0.70 moles per liter of ammonia gas. Remember, we have to take the moles of ammonia gas and divide it by the volume, 5 liters. And there were no values given for our products, so initially we will assume they are 0. They then give us the moles of hydrogen gas at equilibrium, which we then have to divide by 5 liters to get concentration. Once we have the initial and equilibrium values for H2 gas, we can determine the change. When we have the value of one change, we can use stoichiometry to determine the change of all other species in the chemical equation. Here we have the change of all species. Remember, if the products have a positive change, then the reactants must have a negative change. Now we can take our initial concentrations, add or subtract the change to get our equilibrium values. We can then put our equilibrium values in the Kc expression, which is again the products over the reactants. As a result, we get a Kc value of 1.9 times 10 to the negative 6th at flask temperature. That means Kc is less than 1, therefore the reactants are favored. Example number 5. Initially, 2.0 moles of CO2 gas and H2 gas are introduced into a 1.0 liter container. What would be the equilibrium concentrations of the reactants when the Kc value is equal to 35 at 1,823 degrees Celsius? Pause the video and attempt this example. First, we have to create an ICE table if we want to determine equilibrium concentrations. They are giving us the initial concentration of both reactants, and since there are no values for the products, we can assume that they are zero. Unfortunately, they are not giving us an equilibrium concentration. So right now, we will have to assume that the change is an unknown variable. The unknown variable will be x. Since we're starting with all reactants, the reactants must lose. Therefore, they will be negative x. And since the products are starting at 0, they have to gain. They will be positive x. And at equilibrium, the concentration of our reactants is 2.0 minus x, and the concentration of the products will be plus x. We have to determine the value for x. We can first write our Kc expression, which is equal to 35. And remember, both products are equal to x, and both reactants are equal to 2.0 minus x. We can square the Kc value, square the concentration of the products, and square the concentration of the reactants. This will leave us with a value of 5.91 ... is equal to x divided by 2.0 minus x. We can assume that the 5.91 is over 1 and cross multiply, which leaves us with 5.91 times 2.0 minus x, which is equal to 1x. We then have to FOIL the left side of the equation, which means we will times 5.91 first by 2.0, then by minus x. That leaves us with 11.83 minus 5.91 x, which is still equal to 1x. We now have to bring all of our x values over to one side of the equation. We will bring the minus 5.91 x over to the other side of the equation. It will now be a positive value. That leaves us with 6.91 x on the right side of the equation, which we can then divide on the opposite side to solve for our x value. X will be equal to 11.83 divided by 6.91. X will be equal to 1.7 ... Well, we can now determine our concentrations of both reactants and products. Remember, the concentration of both reactants was equal to 2.0 minus x, which will now be 2.0 minus 1.7 ... The concentration of both reactants is 0.29 moles per liter at equilibrium. Again, this is known as a difference of squares method, and this will be the only method we will use to solve for x in a Kc expression. Moving forward, we will explore complex Kc expression problems.